lunch break. I know that it's hard, maybe you're a bit sleepy, and for that reason, I have a present. So I have a Lego set with me, and by the end of the presentation, I will ask a question. Whoever will answer the question correctly will get the Lego present. So maybe that's the motivation to stay awake. um, my name is Florian, and I work for a company that's called Flatiron Health. That matters for this talk because what we do is we build a data platform for cancer research. And doing that has a lot of challenges, and I basically want to walk you through some of the challenges, why we do this, and how we solve those challenges. So first, I want to explain you what real-world evidence is. So these are the data we are dealing with, and why it's important. Then I will make a case that's not so easy to do, so don't try to do it at home. It's not trivial. Then I will talk about feedback loops. So what makes development slow? I will introduce some part of our technology stack, like as the engine of our feedback loops. And then, like the main part of the talk, I will introduce some of the patterns that we apply to speed up the feedback loops in this complicated environment. And lastly, I want to close with a summary on the impact of real-world evidence generation and the treatment of cancer patients. Okay, let's start with what real-world evidence is. So before I joined the company, I never heard about this, so I don't assume that anyone else knows, so I'm going to explain that. So the idea of real-world evidence is that you take data that's already available in operational systems from hospitals, from state-run cancer registries, from laboratory systems, and turn this kind of data into research-grade data sets. So we're talking about systems that really are like store data for insurances, they store free text fields, and what we do is we process the data to extract variables that have a high quality so that they can be used for medical research. And the reason why you do that, I think there are several good reasons. The first thing is like drug development is expensive, especially in the area of oncology. We're talking of hundreds of millions up to billions of dollars that it costs to develop a new cancer drug. Data is not the only reason that makes this expensive, but an important reason, because you have to do a lot of clinical trials that are very important, and real-world evidence can replace many clinical trials. The second advantage of real-world evidence is that it captures real-world treatment data. So not from experiments, but like from data from everyday cancer care. And the last part, this is also very important for me, is that we are able to create data sets that have diverse population groups. Why this matters is that people that are unfortunately diagnosed with cancer nowadays, they have a much higher chance to survive and after the treatment have a good life than 20 years ago. 20 years ago, the chemotherapy destroyed cancer cells and all the cells around it as well. Nowadays, the treatment is much more targeted, which is very good, but comes with a price because modern treatment is really dependent on different population groups. So modern drugs behave differently amongst different population groups. This is why it's so important that we are able to have data from people from the US, from Europe, from Asia, and Africa. So I hope I could explain you somehow what real-world evidence is and maybe convince you a little bit that this is a good idea to do that. And now let's cover the part why it's not so easy. So first, so the systems you're dealing with, they are not built for capture research data, right? They're built for, sometimes it's paper, right? We have servers in basements. So like in my first integration, I installed a server in a basement. So not a data center into a dusty basement. There are no standards. I mean, there are standards, but a million different standards. And often, the hospitals and the clinics, they don't use any of those standards. So for example, we have a million different file formats from scanned documents, PDFs, XML, JSON. They all represent different standards. There are healthcare standards, really a lot of them, but often, the systems don't implement them. And often we don't have an exchange format at all. Sometimes we need to grab the backup of a database, so we deal with internal database structures. So that is really hard to do. Next reason is when you are able to still access the data, you deal with very messy data. So most of the data is captured somewhere or hidden somewhere in documents. I have an example. I mean, this is generated by ChatGPT, so it's not real patient data. But this is a good example of how it looks. So like it's often notes that the doctor writes down, today is Monday, the sun is shining, the patient told me that they're not feeling well. By the way, I administered those drugs. Hey, the patient had a bit of headache, right? This is kind of the data we're dealing with, from which we have to extract structured information. And the last, also very important reason is, of course, we're dealing with very sensitive data. And for that reason, of course, like privacy and security is a major concern for us. And in order to still be able to implement such a system, we have a probably quite complicated architecture that somehow looks like this. So it's not one data pipeline, right? It's not that we load the data into the cloud, tell our data scientists, here's the data, and then we have our data sets. We have a lot of fragmented environments. And what we implement is a concept, what we call that we increase the privacy. It's a privacy-enhancing data processing. So we have different zones where with different privacy levels. And by the end of the processing of the data in each zones, we make the data more anonymous. So for example, the first step is always removing direct identifiers, replacing like the IDs from a clinic ID with synthetic IDs. But then you have data that you couldn't be able to tell anymore who it is, but with statistical methods, you could still, draw conclusions. And we cut more and more of those properties, for example, like shifting dates around, so that we still capture the statistical properties of the data, but by the end, the data is anonymous. And the last stage is that we have run our own platform for our life science partners. So we have a controlled environment. It's a data platform, with notebooks and so on, so that they can actually work with the data. But it's an environment that we control, so that we make sure that they don't link the data to external data sources. Okay, but you can believe me, that's like the system architecture is complicated, and not for like technical reasons in a way that this allows us to process the data in a secure, privacy-enhancing way. Okay. I hope everyone is now convinced that, oh my God, is that hard to do. So next I want to talk about feedback loops. Another characteristic of our data is that the most important people in our company are clinicians. I don't understand the data, right? I'm not an oncologist. I didn't study medicine. So, and this is like a level of domain that you don't understand by reading 3 papers, right? So we have a lot of clinicians that bring in the medical expertise to help, like set the direction for research and to evolve our data models. And simply to look at the data and tell us, does it look correct? Of course, they interact closely with our data scientists. But there are also people like me that are more on the engineering data architecture side. They're also part of this feedback loop. So we have like a feedback loop that spans several functions, often several teams. All of that, okay, maybe you can still see that all of that in the technical system with very fragmented systems with strong boundaries. And you're probably not surprised when I tell you that slows down development a bit, just a bit. Before I want to explain to you the patterns, how we still are able to speed up our feedback loops, I want to explain you the tech stack that we are running. And then I'm coming to the patterns, how we use this tech stack to improve the development speed. This is now the Lego, and now I'm proud, now I'm switching to the present. I'm not asking a question yet, but I'm proud of what I chose. So I'm using Lego bricks to display the architecture. And we have a team in London. So having a Lego architecture set for London, isn't it a great choice? So, okay, so coming back to the slide. So most of our pipelines run on AWS. Many of our pipelines use Dexter as orchestration framework. And we use DLT for ingesting the data. Does anyone know DLT? Okay. That's very cool that some know, but it's even better that not many people know that. Whenever you have to move data around, right, in a Pythonic environment, look at DLT. It's amazing. It's basically an ingestion platform as a library. I will show you how this looks a little bit. And we use dbt heavily for our transformations. Like DLT and dbt somehow have the same mindset. And most of our compute runs in Snowflake. Okay, so let's implement such a pipeline. So bring up a terminal. First, we install all the dependencies that we need. So we install DLT, we install DBT, we install Dexter, and we install IBIS. Why we use IBIS? IBIS is an abstraction over Snowflake. Why we use it, I will explain later. So then since we use Dexter, we need some sort of pipeline file. So we create a pipeline Python module, and then we declare our DLT sources. So DLT brings some decorators with it. So we basically have a function that points to S3. We use a built-in function, this file system function, and with that DLT will read all the data chunk by chunk from S3. And we implement our own DLT transformer, because we have very specific file formats that no one else cares about. So there's no open source transformers for these. But this is just, we're talking about 30 lines of code. To basically take those, in this case, BDT files, it's a medical exchange format, and turns those files into JSONs, because DLT understands how to normalize JSONs. And with that, DLT is able to generate nice tables in our data warehouse. Then we jump to BDT. So the data that's ingested via DLT is represented in our DBT pipeline as DBT sources. So we have a YAML file. We basically reference the tables that are generated by DLT. Of course, in production, we generate those source files, but here I just, for simplicity, I typed it out. Then we implement DBT models, for example, like a lab table for the John Doe clinic. And often, like when we deal with structured data, there is some sort of like a shared format. In this case, it's a BDT format. In those cases, we use DBT macros. So DBT macros are reusable SQL snippets. So that allows us every clinic that gives us some file in the BDT format, we can use this macro to extract, for example, in that case, the lab values. A DBT macro is implemented as a SQL file in the macros folder with a special syntax. So you wrap it in those in this macro keyword, and then this is now just SQL, right? This is just a SQL that runs the transformations. Okay, and now let's wire everything together as into a Dexter pipeline. First, Dexter has a very great DLT integration, so it brings up a decorated DLT assets. We basically pointed to the DLT sources you implemented, chain it together with the transformer, and then you tell DLT, by the way, write all the data to Snowflake. And that's enough to get the data from S3, the files from S3, pass the data, then DLT normalizes the data, so unnests the data and creates a nice table structure, and in the end loads the normalized tables to Snowflake. Then DBT takes over. So Dexter has an equally nice DBT integration. So we use some classes, DBT project, where you basically point Dexter to the DBT manifest, which is kind of metadata about your DBT pipeline. And a CLI resource where we configure Snowflake as the profile. What this does, I will explain later. And then again, we have some decorators, DBT assets. And we tell Dexter that those DBT assets depend on the DLT assets, so the Dexter is ordered to execute the pipeline like this, the assets in the correct order. With that in place, we can also just write some arbitrary Python code as our own Dexter assets. Here we basically write a code that is dependent on the, we tell Dexter that this is dependent on the DBT model, so the Dexter again runs the nodes in the correct order. And we read data from Snowflake via IBIS. So IBIS is does anyone of you know IBIS? Also, like for the ones who don't, go check it out. It's the project tries to find a standard for data frames. So it's an abstraction over many technologies that have a data frame API. For example, Snowflake. And why that matters that we don't talk directly to Snowflake via IBIS, I will explain later. And there's also this nice function to pandas batches that really chunks up your data in the data warehouse and then streams all the chunks of the data, so you don't have any memory issues that you load 2 terabytes of data into memory. This is a very built-in function that's very nice. So this is a custom written Dexter asset, like just Python code. We still represent this Dexter asset as a DBT source by writing a DBT source file. And we need to tell Dexter somehow that how this Dexter asset is connected to our DBT source. And for that, we use a special meta tag where we say, okay, this is the asset key. So again, that Dexter knows how to execute everything in the correct order. Okay. The last step of wiring everything together is we create a definitions class where we reference all the assets that you have and then wire in the resources. So DLT resource and DBT resources come out of the box. The IBIS resource we need to instantiate ourselves with, and we pointed to that. We say that use Snowflake as a backend. And then we run the pipeline. So first we run DBT compile, and then we execute the Dexter job. Dexter has a of course, like a daemon server, and Dexter can run things on a cluster. But in this configuration, it runs locally. I mean, locally wherever locally is, but it doesn't need any additional server. It doesn't need any additional infrastructure, which is a very nice feature. And it's an easy migration path from running things locally to running things on an orchestration server. And all together, that looks like something like this. So we have DLT that reads the BDT files from S3, transforms them into a better looking JSON structure. Then DLT automatically normalizes those JSON files, creates files. I think it's Parquet files, but I actually don't know. And then loads those files into Snowflake. Then DBT takes over, applies all the transformations. Then Dexter runs a custom asset for the harmonization that we just showed you as an example. And then we have our final table. Okay. Does any one of you use Dexter, by the way? No one. That's okay. Let's also go check it out. Like, those technologies together is a dream team. So that's a dream team. Okay, then let's talk about patterns that accelerate a loop. So as you remember, we have like those feedback loops. So we run those pipelines to generate data that clinicians have to look at, right? It would be good that this doesn't take days, but more seconds. How can we achieve that? The first approach, like a first principle, is shifting testing left. I had a talk earlier today about data testing with DBT. Did anyone attend this talk? Okay, very nice. So I have to skip a little bit the slides because I have 7 minutes left, so I'll be very fast. We think about testing with like this classical software engineering style test pyramid, where we want to have a lot of unit tests, some integrity tests, regression tests, and for the final data, some cohort tests. And I'm going to show you how the cohort tests would look. And this is another good reason why we represent a Dexter asset as a DBT source, because then we can run DBT data tests on data that is materialized via Dexter. So we have a DBT source where we basically specify this is the table, and then we add a new section, a column section, where we have a test column. And so test is not a data test, it's like a lab test, you know, like a biomarker test. And then we can run a cohort run test. So this is a macro that we wrote ourselves, right? Expect row code quantiles to be greater than or equal to. It's in the end some SQL code, and it has some parameters. So first we specify a filter, like we select certain lab tests. Then we have a cohort filter, meaning we select patients that belong to a certain cohort, and then we assert a statistical distribution. This test can look like, for all multi-monomer tests, we expect that at least 70% have an M-spike test, because we know this is the treatment standard. And if we don't have enough of those biomarker tests in our data, something is fishy, right? Either transformation logic is wrong or we're losing data. So tests like that. Okay, that's the first important pattern. The second important pattern is that you want to enable prototyping. In an environment where data scientists and clinicians can sit together, change code, run the pipeline, and look at the outcome. So for that reason, we connect our Jupyter notebooks to the pipelines. How to do that? I mean, there are many tools that you can use. We do it, oh, sorry, I have like the Lego brick animation, I forgot. So what we do is basically we rip out AWS and replace it with Jupyter. I mean, that's not 100% correct, but you probably get the idea. So first we install another dependency, the IPY kernel dependency. We do this so that we can, in the end, create from our project an Jupyter kernel, that when you are in Jupyter, you select the kernel, then you have all the dependency in place. So you can do things like this. So you spin up our notebook. We import the code from our pipeline file. we override, for example, this like this harmonization asset, and then we execute the pipeline from the notebook. So that was the second pattern, that we basically are able to quickly change code, run the pipeline again, see what happens. And now when you think about, that this restricted environments, it would be very nice to do all of that not being forced to do this in AWS or in Snowflake, but make our pipelines portable. And the way how we do that is we in the end rip out Snowflake. So we replace Snowflake with, and that's want to highlight that, we replace it with DuckDB. Does any one of you use DuckDB? Yeah, that's an amazing in-memory or file-based analytical database that can run on your laptop or on an EC2 instance or wherever, and is really fast and can process a lot of data. So how to do that? So we install, the flavors for each of our dependencies, the DLT, DuckDB extension for DBT, as well as for IBIS. Then we spin off our pipeline, and all what we have to change is we tell DLT, by the way, don't write the data to Snowflake, write it to DuckDB. Same for DBT. We have it configured as a profile. We now switch to the DuckDB profile. So DBT will materialize the data in DuckDB, not in Snowflake anymore. And this is now the reason why we use IBIS, because IBIS is an abstraction over DuckDB and Snowflake and many other backends. So we're able to use the same code that runs on DuckDB and Snowflake, but we just replace the backend with a DuckDB backend. And what we achieved by that, so the pipeline that I showed you in the beginning covered roughly that part, right? So going for multiple environments. And with those changes, we are able to move those pipelines to a more restricted data closer to the source, or even to an on-premise system in a hospital, so that we're able to generate first insights very fast and don't have to wait until the data passes for all those stages. Okay. Lastly, I want to close with the impact on real-world evidence generation. And the data set that we provide is widely used. So Flatiron Health, the data from Flatiron Health is kind of the golden standard for real-world evidence data in the sphere of oncology. It has been used in over 1,200 publications, in over 9,000 peer-reviewed publications as well. And I want to quote finally a paper that was recently published, that with this approach, that you're able to provide this data on a global scale. We're able to do this in the UK, in the European Union, in Japan as well, and in the US, so that patients worldwide can benefit by ensuring that the high quality real evidence is available that informs clinical decisions and health policies on a global scale. And with that, I want to thank you so much for your attention. And and the question is, so which database do we use to run those pipelines locally? Oh,
all right, I saw this hand first, so I'll start here.
Is it DuckDB?
Yes, it's DuckDB. Thank you so much. So you're like a proud winner of a Lego set. If you have questions, I'm happy to take one. Else, just grab me outside and yeah.
Right.
Was not a joke. That would be very mean now to say. No,
we still have time for one question.
Okay,
if you want to go for it. Anybody has a question? Yeah, coming.
Yeah, just going back to the difficulty of collecting that real world data. How do you ensure patient privacy while you're also I assume you have to track patient history across like multiple hospitals or whatever other treatment things. How do you just manage that, just out of curiosity?
That depends. So the simple answer, we don't. It depends on the care setting. So in the US, there is actually a service that allows you to. What we always do first, we create synthetic IDs. And in the US, there's a service that allows you to create synthetic IDs to link patients together. In Europe, this is not allowed. But in the setting, so for example, in the UK, patients stay at the same hospital. And in Germany, is another example where you are treated at your local oncologist, and you're sent back to the hospital for like a surgery, and then you come back, and all the results I mean, this is not a joke. They bring it as a letter, as a printed out letter, and then they are scanned in. So this is why we can, I mean, we lose some data for sure, right? But we still have most of the relevant data within one system. Yeah. But it's a very good question. This would be a hard, and we try to avoid that. So if same patient, so if the same patient is in 2 clinics, we will not see them as the same patient. There will be 2 different patients in our data set.